Cognitive science has historically relied on the von Neumann computer metaphor to explain the brain. This model assumes a central processing unit performing calculations and a completely separate dedicated RAM buffer temporarily storing the data. Neural architectures do not possess this distinct physical hardware. In the brain, processing and memory functions are distributed within and performed by the exact same neural substrate. Working memory operates functionally rather than structurally. It is an emergent property called controlled processing, namely the ability to use activated long-term memory representations to guide current behavior. This network map identifies the three specialized systems that generate this property: the posterior and motor cortex, the prefrontal cortex, and the hippocampus. The ability to hold and manipulate information over time arises from the specific computational trade-offs programmed into the connectivity of these three distinct networks. Building artificial systems that mimic this process requires shifting from models that use external data buffers toward architectures where memory and processing are performed by the same substrate. The posterior and motor cortex, known as the PMC, is optimized for extracting statistical regularities from the environment through slow, integrative learning. As shown here, the PMC achieves this through highly distributed, overlapping representations. Neural clusters activate simultaneously to encode concepts sharing similar features. Because it uses shared nodes, the network can easily generalize from prior experience to new situations. But that same overlapping structure makes the PMC vulnerable to interference. It cannot isolate a single representation from the rest of the network's activity during a delay. A network wired for broad generalization is structurally incompatible with the need to hold one specific isolated memory state active. To maintain a memory without constant input, a network relies on recurrent excitation, loops that feed a node's activation signal back into itself. To see why the PMC fails at this, consider a network mapping three items: a synthesizer, a terminal, and a television. They share three central feature nodes: a keyboard, a monitor, and a speaker. When we activate the synthesizer subnetwork and apply a recurrent loop to hold that memory, the activation begins to move through the shared nodes. Because the nodes are shared, the recurrent signal inevitably bleeds into the pathways for the terminal and the television. Within moments, the activation spreads until all three items are firing simultaneously. This structural interference effectively erases the original, specific memory of the synthesizer. Any system relying on overlapping distributed features will corrupt its own data if it attempts to use simple recurrent loops for maintenance. The prefrontal cortex, or PFC, is specialized to solve this interference problem. This map shows the PFC's solution. Instead of overlapping, the PFC uses isolated, non-overlapping clusters of nodes. Each cluster has its own self-contained recurrent loop. When an isolated PFC cluster activates, its internal loop allows it to maintain that firing state indefinitely. Because there is no overlap between clusters, the activation cannot bleed into neighboring nodes. This isolation provides the robust maintenance needed to hold goals and instructions active, even in the face of distracting information. This reveals a structural trade-off. Optimization for inference requires the dense connectivity of the PMC, while optimization for maintenance requires the isolation of the PFC. A single network cannot maximize both. However, if the PFC's loops are strong enough to resist interference, they also block the network from being updated with new information. This gating paradox is solved by the ventral tegmental area and its dopamine projections, which act like a biological valve for the PFC. Baseline levels of dopamine keep the PFC gate closed, protecting the current memory from being dislodged by sensory noise. A phasic dopamine spike opens the gate. It temporarily amplifies incoming signals from other brain areas, allowing them to overpower the PFC's internal loop and updated state. When the spike subsides, the gate closes, and the newly updated information is locked back into active maintenance. Because PFC representations are isolated and combinatorial, each active item requires its own dedicated, non-overlapping cluster of neurons. This lack of node sharing creates the capacity limit. There are only so many independent loops available to hold different goals simultaneously. Routine memory is not managed by a central executive commander, but by a neurochemical gating system that regulates which signals are allowed to update the network. To see how these systems interact, we use the AX continuous performance test. The rule is simple. A subject must give a target response only when the letter X appears immediately after the letter A. If the subject sees an X without the preceding A, it is a non-target. This makes the X stimulus ambiguous on its own. Success requires 3 steps: encoding the cue, maintaining it through a delay, and using that memory to process the probe. This task isolates the system's ability to update its state and use that maintained context to bias behavior. The trial begins with the presentation of the A cue. This architecture shows the encoding phase. The PMC identifies the A and updates a specific PFC cluster. During the delay, the A stimulus is removed and the PMC node goes dark. But the isolated PFC node continues to fire, maintaining the context. Then the ambiguous X probe appears. The PMC identifies the X, sending ambiguous activation to both the target and non-target response nodes. Simultaneously, the maintained PFC node sends a top-down bias signal based on the A it is holding. This bias combines with the X signal, providing enough activation to push the target response node over its threshold. As the target node fires, lateral inhibition suppresses the non-target node to ensure a clear behavioral response. This demonstrates how controlled processing can emerge without a central commander. It is the result of a self-maintaining PFC representation, providing a constant top-down bias to the shifting activation patterns in the rest of the brain.